All right, good afternoon, everyone. Let's take a look at your work from yesterday dealing with review and extension of your factoring skills. I had mentioned yesterday that you have these two very important tools, one of which is factoring, the other of which we're going to be talking about today. Because not only, and this came up yesterday, not only do these tools allow you to evaluate when an expression is equal to 0 and when an expression is undefined, which we talked a little bit about yesterday, these tools also allow you to simplify expressions. And in math, there's a reason why we call simplification simplification. It's because working with a simpler problem is easier. That's why we simplify. So this was on page 3 of your textbook, question 1, 2, and 4. Question 1 is really basic, I would say grade 10, 11 factoring. Same with number 2, except for number 2 extends into the realm of differences of cubes and sums of cubes. And then number 3 is something that in principle you know how to factor these things, but you've never been expected to factor things with fractional exponents before. And when it comes to the real world, which is what calculus is about a lot of the time, you can't get away from fractions. Okay. Does anybody have any questions you would like me to go over? Go ahead. 4F. Okay. So we have x squared plus 1 raised to the 1/2 plus 3 times x squared plus 1 raised to the negative 1/2. I want to start here, Christy, by just saying to you, if I had a to the 1/2 plus 3a to the negative 1/2, that's something that we ought to be able to factor. What, as of yesterday, what cranks this up to the next level is the fact that it's not a. But if I were asking you to factor this expression, then you would say that I'm going to factor out a raised to the negative 1/2. And you're taking out a because there's an a in each term, and you're taking out a to the exponent of 1/2, negative 1/2, because negative 1/2 is the smallest exponent. This is the rule that works. And then what you do is you write, we're going to write a plus 3a, and we're going to have to put exponents on each of these. And what we normally do to find the exponents, well, what we normally do is not much. We just look at it and go, oh, a 3 goes there or a 5 goes there. But when it becomes exponential, it's more complicated. The bottom line is the sum, everyone, of these two exponents has to give you this exponent. Because if I were to multiply this out from the bottom line, I would be multiplying a common base of a, which would mean I would add the exponents. So the question becomes, to what do I add this, to what do I add to negative 1/2 in order to get us to the positive 1/2 where we started? And the answer is 1. I mean, I don't quite know how to teach this at this level. To go from negative 1/2 to positive 1/2, you have to add 1. And that means that this exponent is 1. I'm going to leave this other garbage on here, and I'll erase it later, but that's a 1. And we can just confirm here that if I do multiply these two together, I'm going to have to add the exponents, and negative 1/2 plus 1 gives me the 1/2. Okay. Now, on the other hand, this exponent plus this exponent has to give me negative 1/2. Well, I don't really need a number line there. What is it I add to negative 1/2 to get negative 1/2? I add 0. And I believe that most people would just not even have written 3a to the 0 here. They would have just written 3. Because I'm taking a to the negative 1/2 out of a to the negative 1/2. So this is what we have left. Now what we have to do is, as I said, ramp it up or crank it up to the next level and do the same thing with this. So let me write down what this one is. It is x squared plus 1 to the 1/2 plus 3 times x squared plus 1 to the negative 1/2. So I'm going to factor out an x squared plus 1 raised to the negative 1/2 because there's an x squared plus 1 in each, and negative 1/2 is the smallest exponent. What do I have left? I have left in this, why not? In this large set of brackets, I'm going to have x squared plus 1 raised to an exponent that when added to the negative 1/2 on the common factor gives me positive 1/2 on my starting term. And that's 1. Okay. Plus 3, and again, if you choose to write x squared plus 1 to the 0, that's great. You don't have to. You could just write 3. So we clean this up. We're going to put the x squared plus 1 to the negative 1/2 on the bottom and express it as x squared plus 1 to the positive 1/2, because that's what negative exponents mean. And we're allowed to do that, by the way, because this thing we're moving down is being multiplied by the entirety of everything else. If it were that thing plus something, you can't do that. And then on the top, what do we have? We have x squared plus 1 plus the 3, so you have x squared plus 4. So the numerator will be x squared plus 4, the denominator will be x squared plus 1 raised to the 1/2. Just a housekeeping kind of thing. Could you write this? Yes, but we don't. This is more valuable to us mathematically. At some point you can think of it as a square root, but you don't have to. Well, no. You have to be able to think of it as a square root, but you don't have to write it that way. Does that help? Okay, does anybody have any further questions? Okay, so today's lesson is dealing with rationalizing. And every time I teach this lesson, I look at the lesson I've made, and it has only 2 examples, and I think, man, we're going to be done early, and you guys will be done all your homework early, but the problems that you're assigned get more difficult. Okay? So we're looking at rationalizing here, and I will remind you that I don't know when it is. I think it's in grade 11 math, that you're introduced to this idea that something like this is verboten. We don't do that. We don't like radicals in the denominator. And there's a reason why we talk about getting rid of radicals in the denominator, but at this level, there's nothing unique about the denominator. We may want to get rid of a radical in the denominator, or we may want to get rid of a radical in the numerator. It depends on our needs, and this is the biggest change from Math 30 to calculus, is you're going to do math depending on where it takes you. You're not going to see a quadratic and assume, well, I'm just going to factor it because that's what we always do. You're going to factor it if it leads somewhere. So what you have learned in Math 20-1 is that if you have a monomial radical that you want to not have, you multiply the numerator and denominator by that radical. So we would get 3 root 2 over root 2 times root 2, which is 2. You could certainly make the argument, and I would argue it, that this thing we started off with is simpler than this. And yet in Math 20 it's simplify, and we're automatically assuming that rationalizing is simplification. It may or it may not be. And again, we will get rid of the radical in the denominator if we want to. And we will get rid of a radical in the numerator if we want to. By the way, it's interesting because if I have 3 root 2 over 2, and I say get rid of the radical in the numerator, you would multiply the top and the bottom here by root 2 over root 2 and get 3 times 2 over 2 root 2. Root 2 times root 2 is 2. Oh. You get 3 over root 2. I mean, you could just go back and forth all day if you want. But my point is really important. You rationalize whatever you need to make things happen. However, we're going to be rationalizing binomial denominators. I mean, might you encounter a radical that's a monomial in your work in calculus and have to rationalize it? Yes, but we're focusing today on radicals like root a minus root b. That could be a denominator that we want to get rid of, or it could be a numerator that we want to get rid of, right? It depends. And you'll see later on how that works. Well, it turns out if you want to rationalize that radical, you need to multiply the numerator and denominator by its conjugate, which is root a plus root b. Don't confuse this with differences of squares. Don't confuse this with negatives. It is a difference of squares, so I misspoke. Don't confuse this with a minus b and b minus a. Those are negatives of each other. So why does this work? The reason it works, and by the way, these are conjugates of each other, right? So the conjugate of root a minus root b is root a plus root b. The conjugate of root a plus root b is root a minus root b. And if you want to get rid of one, you multiply top and bottom by the other. So they're conjugates of each other. I say, of course, this results in a difference of squares because I feel as though you should understand why this is going to work from grade 11 math. That if I multiply these together, what I have to do is FOIL this out, and root a times root a is a. So the fact that we had two radicals in what we call the first positions for FOIL that are multiplied together, and the fact that they're the same radical means you're squaring a radical. You're taking root a and squaring it, and that gives you a. No radical, rational in other words. My outer radical arithmetic says root a times root b is root ab, and it's negative. My inner, because they're conjugates, will be the opposite of that. So even though these two products in the FOIL are irrational, they cancel each other out. And then last will be root b times negative root b, which of course is negative b. And the point is you get that, and that's rational. There's nothing particularly special about something being rational in our work, as much as it's that it will probably cancel with something else. Rationalizing is a way to simplify. All right? So, rationalize the numerator of this expression. Why? Why not? There's a radical in the numerator. Let's see what happens when we get rid of it. So I always recommend rewriting these. We have root x plus 3. That radical extends to just over the x, and it doesn't go to the 3. This is over x minus 9. So I'm going to rationalize the numerator by multiplying the numerator and denominator by the conjugate of the radical numerator. I hope it goes without saying that the reason, as he says it, that the reason why we multiply the numerator and denominator by that is we don't want to change the value of the quantity. And root x minus 3 over root x minus 3 is 1. We're not changing it. We're just multiplying by 1 effectively. Now this is going to be very similar to rational expressions and a general rule I've told you in rational expressions, which is that when you're working with rational expressions and you maybe bring two rational expressions together with a common denominator, you leave the denominator in factored form in the hope that something will cancel, because you're only ever allowed to cancel factors, right? You can only, I want to start off with that actually, that the only way you would be able to cancel the b with the b here is if b is a factor of the numerator and b is a factor of the denominator. That's the only way it will work. So that's why we don't expand, say, the numerator or the denominator when we're working with rational expressions sometimes, because we want things in factored form. However, let's say it's a rational expression problem where we have a common denominator that we've created in factored form. We can't tell that the top factors unless we simplify it first. And the idea here is the top of this will simplify. We have to multiply it out because that's what we're asked to do, get rid of the radical. And what you get is x minus 9 on the top. Just think about that for a second. You get root x times root x, which is x, and you get 3 times negative 3, which is negative 9. For this, I mean, I've taught you all this, so I'm sure you've probably heard me say this. For this, you do not have to FOIL. You can just FLA, right? Because the outer and inner are going to be opposites of each other. So we get x minus 9. Well, that's brilliant because we have an x minus 9 here as a factor. And we have an x minus 9 in the denominator and the numerator, so they cancel. And what am I left with on the top? 1 over root x minus 3. And the bigger picture, everybody, is this. When you look at the original expression, there was a radical in the numerator. We didn't get rid of it because we don't want radicals there, because if that's your philosophy, well, then you end up with a radical in the denominator, right? We didn't do that to get rid of radicals. We did that to get a simpler expression that might be more useful. And I want to talk more about that in maybe 10, 15 minutes. But does anybody have any questions with that work? If our job was solely to get to this point because we can use this for some purpose, then we didn't have to pull out the rationalization tool. We could have pulled out the factoring tool. This isn't always going to be the case. But I could have said, you know what? X minus 9 is a difference of squares. X is the perfect square of root x, plus or minus. 9 is the perfect square of 3. Now, you're not always going to notice that, and it's not always going to work. But in this case, it does, nice and cleanly. You're left with 1 over root x minus 3. And again, it could be that it's just, we want to be able to get to that expression because it has more usefulness to it. And I know that's kind of cryptic right now, vague. But as the days go by, you will understand more and more what I'm getting at. In fact, at the end of today's lesson, I have a couple of challenge problems for you that illustrate the point. B, second example. So rationalize the denominator of this expression. I mean, let's face it. If I said to you, rationalize the expression, clearly you're going to rationalize the denominator because it's the only one that has radicals. So we have x squared over root x plus 2 minus root x minus 1. It's interesting because I just caught myself in a bit of a lie that I told you earlier. I said we don't write roots. Well, you do if you're working with rationalizations, right? We're not going to put these as exponents of a half when we're doing this kind of work. So I need to multiply the top and the bottom of this by the conjugate of the denominator, which would be root x plus 2 plus root x minus 1. And one of the things you want to be very careful of in this course is making sure when you go from one line to the next that you write things down properly. You know, as much as it's easy to make a mistake in any other math class, here you're going to be confronted with a lot of terms that look the same, both radicals, both have x's, both have 1s, maybe both have exponents of halves. you want to make sure that you copy things down correctly. So I'm just double checking here and it looks good. So now I multiply across the bottom. I'm going to leave this in factored form. Was it plus 2? Yeah. I'm going to leave this in factored form in the hopes, and I can see right away nothing's going to cancel, but that's okay. In the hopes that something cancels. This is over. Again, I'm going to FLA this binomial times its conjugate. When I take the first, which is root x plus 2 times root x plus 2, I get x plus 2. Minus, when I do root x minus 1 times root x minus 1, I get x minus 1. Is everybody fine with that? I hope there's not a single person in the room that is fine with that, because you need brackets around the x minus 1. So what we end up with is x squared, and then the root x plus 2 plus the root x minus 1, and it's over 3. Because x minus x is 0, and 2 minus negative 1 is 3. Nothing cancels, we're done. Okay. Any questions with that example? Now, I mean, today's a day to practice algebra. You're going to see we're done, but I want to discuss a couple of things with you briefly here, and then we're going to get lots of practice with this stuff. And again, every time I teach this lesson, I think, oh my God, there's an hour left? You're going to need it, okay? Most of you will need it. I know that some of you have not taken 30-1 yet, but I still want to talk about something from 30-1 to help those people who have, and to help you who haven't. When you finally do learn this, you'll go, oh yeah, I remember Mr. Way talking about it. If I were to look at a rational expression, or better yet, a rational function like x squared minus x minus 6 over x squared minus 9. We can talk about, and this is for everybody, we can talk about non-permissible values for x, where x is not allowed to be certain numbers. And believe it or not, this is related to what we're talking about, even though this is not irrational. The bottom factors into x plus 3, x minus 3, which means that you have non-permissible values of plus or minus 3. X is not allowed to be 3 or negative 3. Are you with me? Okay. But the top factors as well. And the top doesn't change these non-permissible values. It doesn't. The fact that it's over x plus 3 and it's over x minus 3 means you cannot have these values of x. I don't care what happens. But the top factors into x plus 2, x minus 3. Okay? And for those of you that have taken Math 30-1, you know that even though you're not allowed to put 3 in, you would like to put 3 in because it will tell you something. It will tell you the y-coordinate of the whole. Okay? For those of you who have not taken Math 30-1 yet, or you're in it right now, the fact that you will never be able to put this negative 3 in, it will always result in division by 0, is not my point. We cannot put 3 in because we'll be dividing by 0, but you know what? If we do that, now I can put 3 in. And the only thing I want you, if you're taking 30-1 right now, to understand is what you get when you put 3 in is information. It tells you something useful. And in calculus, we're going to start this Monday, Tuesday of next week. That's what we're always working towards. We're always working towards an expression and putting a value of x in. And if it doesn't work, we want to massage that expression and change it so that we can put that value of x in. Okay? And you can arrange it so you can put that value of x in, which you're not allowed to, but gives you information anyway. You can do that by factoring and rationalizing, okay? Are you with me on a general math philosophy here? Okay, so for that reason, I have the challenge problems I don't want you to do until you've worked on number 1 and 2. But I have 2 challenge problems, and in fact, I don't even want to give you the answers. The problem is this. You cannot put 8 in here. You cannot. Because if you put 8 in here, the cube root of 8 is 2, and 2 minus 2 is 0. Now, I'm going to give you all a little tip for later. You will know that it's 99% likely that you can simplify it to put this number in. Not always, there's an exception. If you get 0 on the top and the bottom. And that might make sense to some of you from Math 30, because if that's the case, then you have identical factors. But what this question is asking is, do something to this so that you can put 8 in. And what this is asking is, do something to this so that you can put 2 in. Because what you get when you do that and put 8 in is valuable. Tells you something about that expression. It's not really a y-coordinate of a whole, it's something different. Okay? So I'm going to leave this up here, but I do not want you working on those challenge problems first. By the way, you cannot simplify this by rationalizing the denominator. That trick only works with square roots, not cube roots. You have to do something different here. The bottom one, number 2, you can simplify by rationalizing. It's a little more complicated than just that. But the top one is going to require factoring somehow. So I'm going to leave these up. I want you to crack the books and get started on questions 1 and 2. And even when you look at 1 and 2, it doesn't even look like there's a lot of questions there. But look at some of the work you did yesterday, right? Look at all the pencil on paper work. It's extensive. Get started. I want to just take my attendance and do one other thing at my computer, and then I'll be around to help you out.